The one place that a gap would form is if you have the big detachment and it's sliding along. It would form a gap like this if the rock were 100% perfectly rigid and didn't collapse or bend or anything. However, we don't form gaps. It doesn't happen. If this fault is 10 kilometers deep, that's 10 kilometers of rock. That's thick, that's heavy. The rock is not that strong. What happens is it never even gets to form this gap. As it's moving and sliding, it's collapsing at the same rate, and what we end up with is this rollover anticline. This is an example of a monocline. We saw one photo of a monocline back when we were talking about anticlines and synclines, where it has one tilted limb and the other side is not tilted. This is a primary way to get a monocline. We see on the right hand side of this rollover anticline, there's no tilt. On the left hand side, there is tilt, so the left limb is tilted. So that's a basic rollover, but the Earth doesn't like to be really basic. We can see on a small scale, like a single outcrop, it looks, hey, we've got a rollover anticline, it's just like the textbook. But if the rest of this wasn't eroded, we might see something more complicated. Like this, where it was actually a series of listric faults. So we had a rollover anticline right here, and another one due to collapse here, which resulted, since this was continuous, in a rollover syncline. So now we've got an anticline and a syncline, all because of collapse. No compression. So anticlines and synclines don't have to be from a compressional stress regime. They can form in an extensional situation because of gravity. Gravity causing the rock to collapse down, resulting in anticlines and synclines. Can also result in more faults. Sometimes instead of just bending and folding, the rock is brittle enough that we get multiple faults. They fall into two categories: synthetic and antithetic. Synthetic faults are basically feeding into the primary fault. They're in the same general direction, and they just help the rock extend in that direction. Antithetic faults, on the other hand, are in an opposite direction. So we can see this big fault swooping down and to the right, and this antithetic fault swoops down to the left. It's caused by slumping. The rock was just not strong enough, or rather, I guess it was strong, it was rigid, but it wasn't plastic enough to fully fold and bend over for that rollover anticline. Instead, the rock bent partway and then broke. And so we get this slumping, we get this antithetic fault, and this antithetic fault, and they're in a different direction from the primary fault due to rock collapse. And then we can get really, really complex fault systems, where we have a little horst out in the middle here. Horst because it's got the two normal faults going away from its center, plus the cowboy could sit on this just fine. So we have this little high out in the middle, and we have two basins on either side. They're basically called subbasins because it's split by that high area in the middle. We have synthetic faults, we have antithetic faults, and we have even more faults underneath, called an extensional duplex. So the real-life rift systems are quite complex. They have lots of different kinds of faults. They have grabens, half grabens, horsts, slumps, basin fill, all kinds of things going on. If we look at an extensional system across a long area, we can see multiple types at different points along the way. So we have, you notice this upper and lower plate. I'll explain that in just a moment. But you have half grabens that are tilting east. You have some that are half grabens that are tilting west. We have some places where it looks like you have a rollover anticline facing west, some rollover anticlines facing east, some areas that seem to have a rollover anticline going both directions. So multiple types of systems with different orientations can all be part of the same rift area. So the upper and lower plates, what we mean by that is which is basically the footwall side is the lower plate and the hanging wall side is the upper plate. So if we flip back here and we see, okay, here's the rollover anticline and these blocks. So this is the upper plate, this is the hanging wall, and this one is the footwall that's underneath it. And then we come over here. Here's our rollover anticlines, where my mouse is pointing. And so this is the upper half, and this side has the layer underneath. Basically like this. See, the rollover anticline is always part of the upper plate. And then here it's more even. It's not a true symmetric basin, but we have kind of a little bit of each. We don't have a distinct upper and lower plate because this section in the middle is basically the upper chunk. So let's look at an area, the Cordilleras. This is a metamorphic core province and an example of simple shear rifting. We have the basal detachment down here in B, and it cuts down through the crust to a discrete shear zone. In A we can see it right there. That's the basal detachment. All the little faults of the different blocks meet up and join there. Below it is an area of stretching, the more plastic deformation. The pure shear faulting is entirely in the brittle plastic transition zone. So up here we have other just regular faults, and then this pure shear is down in the brittle plastic transition zone, below which is plastic deformation, above which is the basic brittle Horst and Graben type stuff. Because of that, we can, on a larger scale, see a few special identifiers. We can see that the country rock is non-myelinitic. So the rock didn't contain myelinite originally. However, there is this curved layer or carapace or arch of myelinite underground. This means there was fault movement, grinding the rock really fine, welding it together. That's our definition of myelinite. So we can see where the fault is by seeing where the myelinite is. The basal contact is gradational. It's not a specific line. And there is fault breccia at the top of this carapace. So we know that the fault has shifted over time. It's ground up a lot of material. We have myelinite, we have breccia, we have this transitional gradational basal contact. If we look over at the Basin and Range as a whole, we can see different areas of it, like the Southern Basin and Range, the Rio Grande Rift. The Rio Grande Rift is a very interesting area of the Basin and Range. There's a lot of geothermal energy potential there. And it's an area of current study for a lot of geothermal groups. Over here we have the Colorado Plateau, which isn't all faulted and extended. It's kind of a high, sturdy spot in the middle of all of this faulting. And then we can see to the west is the San Andreas Fault. But the Basin and Range doesn't extend all the way to the San Andreas everywhere, only in this southern area.